of UVM that have been collaborating with us from the start, providing input on sort of what the Vermont food system really needs with regard to agricultural resilience. So agriculture and climate change is a really important topic. We know that in terms of mitigation, which you're not talking about in class, that agriculture emits up to 12% of greenhouse gases, which is a significant contribution. But we also know that climate change is going to have an impact on the production capacity and resilience of agriculture. And that is definitely true here in Vermont with regard to extreme weather. We know from Tropical Storm Irene that the state was largely affected, and many farms were also affected, particularly those that didn't have crop insurance and were in floodplains. So part of what we're trying to do here is moving from a disaster relief approach to agricultural resilience in a system that is equipped and prepared for the kind of extreme weather we're expecting to have in this region. So specifically, the objectives of this project are to identify existing farming practices that contribute to both climate change mitigation or adaptation. And we're calling these CCBMPs, which you'll see again. It stands for Climate Change Best Management Practices. What are those practices on farms that help farmers adapt to climate change events, but also perhaps mitigate climate change? We're also interested in assessing farmers' interests in pursuing these farm management strategies under different climate change and policy scenarios. We're looking at improving existing practices and through sharing, outreach, and through policy. And a big part of this project is not just figuring out what those practices are, but also providing decision support for policymakers and farmers. And we're also working very closely with extension and outreach staff to share the information we find through this project so that it's not just research, it's also outreach. One of the things that is really important to Ernesto and myself in the Agroecology and Rural Livelihoods group is a participatory action research approach. So this is an approach that involves researchers and non-researchers engaging in the research process to make sure that the information that's found is relevant and creates change for the good of society. And this is just a general overview of that process. Oops, a little bit faster. So specifically for this project, we're really interested in this action piece. So the action is focusing on what are those climate change resilient farming practices, what are policies that support climate change resilience, and how do we educate not just farmers and people on the ground, but you all who are going to be going out into the world and making this world a better place. How do we provide the information so that everybody can make good decisions about this topic? So that's really what we're focusing on, but we don't really know enough to do this well, so that's where the research comes in. We want to focus on research on farming practices and also policies that are related to agricultural resilience. We're also focusing on outreach and extension. That includes farmer-to-farmer outreach, information for policymakers, and training for service providers who are the people such as extensionists that go out and work with farmers and help them improve what they're already doing on their farms. Part of the participatory action research project is collaborative reflection on the findings. So at multiple points in the process, bringing all of the stakeholders together to say, this is what we're finding. Are we missing something? What would be an interesting direction to take this? And really involving multiple stakeholders in the research process to make sure that it's useful and that we're getting to this action piece. So we hope to be involving the students, farmers, researchers, extensionists, policymakers, ag service providers, and funders in our research and sort of bring them in at different points for feedback to make sure that it's an impactful project. So specifically on the research, one of the things that we did when we first got a little bit of funding was we did a survey of agricultural service providers in Vermont. So these are extensionists, NOFA Vermont staff, people that are sort of a layer above the farmers that are working with them to provide advice and improve their practices on their farms. So we did a survey to find out what were they hearing from the farmers they're working with about climate change. Are they thinking about climate change? Are they thinking about extreme weather? Are they concerned about it? And what do they already know and what are they doing about it? We also did a focus group last May with Vermont food system stakeholders, which included many of these service providers, but also policymakers. We had the Secretary of Agriculture, Chuck Ross, in the room, and a couple of legislators, as well as some funders working on this issue, and a lot of people working in the nonprofit sector around food system issues in Vermont. So that's sort of what we've done, and I can share a little bit of that. Next, we're planning on doing a survey of farmers this winter, and that's really to identify what of the climate change best management practices we're interested in are farmers using in certain watersheds in Vermont. And we're specifically focusing on the Lake Champlain Basin watershed for the first phase of the project. And this will be a chance to find out what farmers are doing, but also what are some of their concerns and what are their interests as far as improving on-farm resilience. Once we identify the climate change best management practices through surveys, we're also going to be supporting that survey with on-farm interviews with key informants. This is really to notice that a lot of farmers are, really all farmers, are entrepreneurs. They know how to do a good job. They know how to support their own business. And many of them are just going and trying things. So we want to go out and interview some of these farmers that are considered innovators to figure out what are the creative things that you're doing that we might not find in the literature that are contributing to agricultural resilience. We also have some of our partners in the Community Development and Applied Economics program are doing modeling around farmer decisions and policy using a mediated modeling and agent-based modeling approach. And what they're doing with that is actually getting farmers and people in the room to look at different climate change scenarios and different policy scenarios to see which ones might turn out to be most resilient in terms of encouraging and supporting farmers to use the practices that will make their farms stronger and more prepared for climate change. And then finally, after we've identified some of these key climate change on-farm practices, we want to go to those farms and do measurement and evaluation of CCBMPs. And this is where the diverse team really comes in. So we have people that are going to be on the ground looking at the agroecology. We have Carol Adair, who's going to be looking at some of the gas emissions and answering some questions we have about the mitigation potential of some of these practices. We also have an economist on board. And that's really important to us. We're the Agroecology and Rural Livelihoods group, so we're not just interested in practices that are good for the environment. We also want to make sure that these practices support farmers making money, which is one of their key goals. So the economist is going to be helping to price out the cost of using some of these practices in their farms to figure out which ones kind of get the most bang for the buck, is sort of how we're framing them. So that's going to be a really important part that's going to be in later phases of the project. In terms of outreach and education, we're hoping to do some workshops on climate change best management practices. These would be workshops for farmers as well as just the general public, for example, at the NOFA Vermont conference. But we really want to focus on farmer-to-farmer trainings and bringing farmers onto each other's farms to kind of share what they're doing and what's working and sort of promote that kind of knowledge exchange. So in that case, we'd be more facilitating and bringing people together to share knowledge. We also hope to hold workshops for policymakers to share what we've learned and discuss how it might contribute to agricultural policies that support agricultural resilience. And then we're currently writing some grant proposals to do service provider trainings. So this would be the people who are working directly with the farmers. And we really want to target not just the typical NOFAs and the extensionists, but veterinarians and seed dealers and those people who are reaching a broader audience of farmers to share information they might be able to pass on to those farmers. And the final piece, which relates to many of you, is that we hope to discuss and advance this project through UVM courses. All of the PIs in the team are teaching courses that may or may not relate to this topic. Ernesto and I teach a community-based participatory research methods course at the graduate level next semester, and we plan to bring this project in as a service learning project as part of that course and hope to get some student energy to help advance it. It's really important to us. So this is just in closing. The service provider survey that I mentioned earlier provided some information about what service providers were hearing from farmers. And this was a really encouraging takeaway. they were saying that farmers are really armed with sufficient information, but they're just not supported to act on that knowledge. So this kind of dispels the myth that the university has all of the knowledge on this topic. We really believe that the farmers have a lot of information. It's just a matter of supporting them and creating mechanisms for them to share information with each other and with policymakers to expand the work that's already being done. So here's a link to more information about the project if you're interested. I've also left a couple of cards there if people want to follow up, and I'd be happy to take some questions.
Thank you.
What kind of farmers are you talking about? You talking about dairy, fruit, poultry?
We're still narrowing that. We'd love to do all. I'm not sure it's realistic. I know that dairy is definitely going to be a part of it just because they're a huge portion of the agriculture here in the state. But we're also talking about veggie growers, and many farmers are diversified. So we are looking at practices that would be applicable on a diversified farm.
Can you give examples? I apologize if you already did because I came in late, about some of the CCM BMPs that you're interested in looking at, either ones that you think might have the largest impact in terms of greenhouse gases, or the ones that you think farmers might be the most interested in adopting?
I can't speak knowledgeably to that. We're actually working right now on a really broad lit review to figure out what practices are popping up in the literature, and then we've been talking with kind of key informants. And in the conversations that I've had with key informants about this project, you know, we're hearing things like tile drainage as a really effective new technology for dealing with drought. There's always the, you know, stream bank, riparian buffers that reduce soil erosion. Those kinds of practices. But that's kind of the phase we're in now, is figuring out what are the promising practices, and then let's evaluate them for the Vermont landscape and figure out which ones to support more. Yeah, thanks. Other questions?
So when you think about these best management practices, do you have a time frame in which they exist? So we have different scenarios of how climate change may manifest itself on the landscape. And those scenarios are based on different emission regimes and how successful we are at curtailing emissions. What scenarios are you using, and how long is your time frame to look at these best management practices?
I can't answer that question. I would say that probably our modelers over in community development and applied economics are thinking more in terms of those time frames. But at this point, we're really just focusing on what are the practices that farmers find important to mention when they think about what I'm doing on my farm to address extreme weather events or those kinds of things. Rachel?
You said that farmers seem to be armed with a lot of information, just need some support to act. Do you know where they're getting this information? Are they investigating things on their own? Is it extension services? Like, what's sort of...
I think the information that they were referring to in that quote is more the kind of information you get from being on the ground outside in the farm from year to year. So a lot of farmers will tell you, you know, like, I've been able to pick my kale like 2 months later than I was 10 years ago, especially people who've been farming for multiple years. So there's just a lot of kind of season to season nuances that farmers are picking up and making adjustments for already. So I think that's the information that they're talking about. It's a great question, and something we've been thinking a lot about. There's actually an article that came out that's in my bag that I'm hoping to read a little bit more in detail, which talks about that in particular. But what we've been hearing and what this article is saying is that many farmers don't necessarily believe in climate change, that, you know, the science or whether or not humans are causing it, they're not interested in that, but they are interested in preparing for extreme weather, and they do believe that that's an important thing to do. So that's one of the things that we're thinking a lot about as we prepare this farmer survey. How do we present the survey? And we're pretty sure that climate change isn't going to be anywhere in that, or the term climate change, that it's going to be more talking about preparing for drought, flooding, pests, the kinds of things that climate change might cause on a farm. Yeah.
Any other questions? Okay. Thank you.
Thank you. Sure. This one, I can hold this while you put that to your shirt.
Figure it out.
This one just slides into your pocket.
Okay. All right. Hi. So thanks again thanks also for inviting me. And I am, like Amy said, new faculty here. I've been here almost a year. So also like Kate, I'm going to be talking a lot about things that I'm interested in and then what I'm planning on doing, less than what I'm actually have already done. And I'm sure a lot of you have already seen figures like this one by this point, showing you just in point of fact that the climate is warming in the last decade versus more historical temperatures, 1950 to 1980, the red being areas that have warmed up. Oh, shoot. Is there a way to make that go away?
Just click on the left again.
Okay, sorry. So we're not only looking at changes in temperature, we're also looking at changes in precipitation, whether that's drought, flooding, or decreases in snowpack, which is a particularly sad one for us here in Vermont. So I am, as a biogeochemist and ecosystem ecologist, which just means that I'm really interested in how things like carbon and nitrogen move into and out of ecosystems and around in ecosystems, like forests and farms. I'm really interested in how ecosystems interact with climate change. And this is a really complex question and requires that we know first what drive ecosystem processes like photosynthesis, like decomposition, changes in temperature, changes in moisture, water availability, and then how climate change is going to affect these processes. And then use this information to predict and manage for mitigation or adaptation, whether this is using models or just simply our knowledge of what happens when you change these drivers. So ecosystems and climate change interact, and how does this happen exactly? One of the things that ecosystems do is affect the amount of greenhouse gases in the atmosphere. And the way that they do this is first by taking carbon dioxide out of the atmosphere through photosynthesis, taking carbon dioxide out of the atmosphere and locking it up in biomass in trees and ultimately in soils. But ecosystems also put carbon dioxide back into the atmosphere through plant respiration and the decomposition of plant litter and carbon in soils. And if ecosystems are waterlogged, if there's not enough oxygen for normal decomposition, you end up putting other greenhouse gases, more powerful greenhouse gases, into the atmosphere, things like nitrous oxide and methane. So how will climate change affect these processes, and then how will these processes feed back to affect the amount of greenhouse gases in the atmosphere, which can either make climate change worse or can make it sort of reduce climate change? So which of these things is going to happen? And this is what I'm really interested in trying to figure out. So to put this in sort of a more basic framework for what I do, we'll look at a terrestrial ecosystem, a forest here. And the two main outputs or outfluxes of carbon into the atmosphere are plant respiration and litter and soil decomposition, or microbial respiration. And this is matched pretty much on a year time scale by the amount of carbon dioxide that plants take out of the atmosphere and lock up in biomass and ultimately in soils. Now we come into the picture when we started burning fossil fuels and putting carbon dioxide into the atmosphere that way, as well as by doing things like burning forests or deforestation. And we know that this has a really large impact on the amount of carbon dioxide in the atmosphere. But if you look at the size of these two fluxes, you'll notice that they're really small. So this suggests that even small changes in these large natural fluxes can have a really big impact on how much carbon dioxide is in the atmosphere. So for example, if climate change, if increasing temperatures increases photosynthesis and plant respiration and microbial respiration by the same amount, we'll see no change in carbon storage either in the ecosystem or in the atmosphere. But if temperature increases respiration more than photosynthesis, the ecosystem will lose carbon, the atmosphere will gain carbon, and the ecosystem's acting as a carbon source. Alternatively, photosynthesis might increase more than respiration, and in this case, the ecosystem is taking up carbon, storing it, and acting as a carbon sink. So these are the sorts of things that I'm really interested in my research program. For example, trying to figure out if ecosystems increase photosynthesis, decreasing the amount of carbon dioxide in the atmosphere, and decreasing climate change. Or alternately, whether ecosystems are increasing the amount of greenhouse gases emitted, increasing the concentration in the atmosphere, and increasing climate change. So here at UVM, I am involved already, thanks to many great people I've met already here. I'm involved in a bunch of different projects, but I'm just going to talk about 2 more in detail today. The first is how will warming affect forests, northern forests? And then the second is a part of the project that Kate was just talking about, looking at how farming practices affect greenhouse gas emissions. So first, how do we expect warming to change forests? We expect first that we'll have declines in snowpack, and this ends up reducing the insulation of soil by snow. So if you no longer have the sort of insulating layer of snow in the soil ends up actually freezing more frequently. So just like last winter, if you walked around, the ground was always hard every time you went out there. So this results in injuring plant roots, the freeze-thaw of the soil. That cycle sort of breaks apart plant roots. It breaks apart those big aggregates of soil, the big clumps of soil you might see that usually protect carbon and sort of keep carbon and nutrients locked up. So these freeze-thaws Yes. But the basic idea is that this results in a longer growing season, and this can have a couple different impacts depending on the way that plants behave. So plants might be able to keep up with these warm periods, the extended growing season. They might stay green and really active through that whole period. And in that case, you'd have this forest, for example. It continues taking up carbon dioxide, it continues taking up nutrients, and you're increasing productivity. Alternatively, maybe the forest can't keep up with these extended growing periods, can't keep up with the warming periods in the winter. So while they're dormant, we might end up with these sort of plant and microbial activity mismatches, where when these plants are no longer actively photosynthesizing, they are no longer taking up carbon dioxide and nutrients. But the microbes, those are my fancy microbes, the microbes have a much shorter spin-up time, and whenever it gets warm, they can sort of be active really quickly. So they'll start respiring and decomposing, releasing carbon dioxide, releasing nutrients, and since there aren't any plants to take up those nutrients, there's a good chance that they'll just be lost from the system. So this could then result sort of the opposite, carbon and nutrient losses. So then the main ideas here, the main hypotheses sort of are that reduced snowpack and soil freezing will reduce productivity, carbon and nutrient storage. The ecosystem or the forest will act as a carbon source, and there'll be nutrient losses. Alternatively, warming could increase the growing season, increase productivity, and store more nutrients so that the forest would be a carbon sink, taking up carbon, keeping nutrients. On the other hand, if plants can't keep up with those warm periods, they can't be active the whole time, but microbes can, you'd end up with this plant microbial mismatch, Where the microbes are going, the plants are dormant. We're increasing respiration, loss of carbon dioxide, and likely also nutrient losses. So to look at all these different hypotheses, I and a couple other faculty members in the Rubenstein School are using a forest mesocosm experiment that was set up in 1994 behind the Forest Service on Spear Street, for those of you who are familiar with that. This experiment has been dormant for many number of years. Right now it's got sort of, all of these mesocosms have the same community on top of them. This is what they look like as of this morning, actually. But we're planning on sort of taking everything out and starting over again to some degree. And we'll be running 2 experiments in these mesocosms, looking at the effect of soil freezing on forests, carbon storage and nutrient losses, or nutrient storage, and the effect of warming 2 to 4 degrees above ambient temperatures on these same factors. So in the soil freezing experiment, we expect to see decreases in photosynthesis, decreases in carbon uptake from the atmosphere, which would increase greenhouse gas emissions and increase climate change. With warming, we're not exactly sure which hypothesis would be dominant, whether plants will keep up with all the warming or whether they won't be able to and just the microbes will keep running. So what will happen, we're not exactly sure. We have some ideas. But that's, again, one of the sort of exciting things about research. We get to figure out which one of our ideas will be right. So the second project that I'm working on here that Kate already talked about a bit was how do farming practices affect greenhouse gas emissions? So the first part that we're working on now, like Kate mentioned, is trying to figure out what farmers are actually doing on the ground right now. Are they, for example, using cover crops? Are they changing their irrigation practices, or are they adopting irrigation at all, I suppose, since this is Vermont and not a dryland ecosystem? Or are they putting in things like tile drains to take water away from their farms when we have these extreme events? So my role in this project is looking at how these different farming practices will affect greenhouse gas emissions. Things like carbon dioxide, nitrous oxide, and methane. And then we'll be attempting to work with farmers to figure out if there's a way that we can manage or adapt our practices to reduce greenhouse gas emissions on farms. So ideally, we'd like to find a farming practice that would increase the uptake and storage of carbon dioxide or carbon in ecosystems, and that would decrease the emissions of these greenhouse gases like carbon dioxide, nitrous oxide, and methane to decrease climate change effects. And then in future work, this is very pie in the sky, but it would be fun to do some experimental work to look at how climate change would affect various farming practices. So those are just a couple of the things I'm working on here at UVM. I'm also working with Stephanie Hurley, who's in plant soil sciences, to develop these on-campus stormwater garden laboratories, looking at how having a stormwater garden or different kinds will affect water quality and greenhouse gas emissions. I'm also working with EPSCoR to model the effects of climate change on the Lake Champlain Basin. And then I've got several ongoing projects looking at modeling decomposition at large spatial and temporal scales. And this is work I'm doing with people at other universities, as well as with actually an undergrad who's here, to continue to progress on this question, which is something I've been working on for a long time. And I had said questions, but I'm not sure if we're doing questions.
Yeah.
But okay, great. So thanks again, everybody.
So climate change is a term that's thrown around today a lot.
Mm-hmm.
Sorry, global warming.
Right.
Climate change, could you more lean towards, like based on your research, like climate change is existing or global warming?
Well, global warming, For me, I usually talk about climate change, I guess, because there are a number of different things that are changing, not just warming. So we've also got precipitation patterns changing, like with the flooding and droughting, floods and droughts, and then changes in snowpack. So I'm very interested in both of those things. And the work that I'm doing so far at UVM is attempting to capture both of those things with either warming experiments or manipulating snowpack, and also the stormwater garden stuff that we're doing. It will be increasing precipitation and looking at the effects of that. Was that the full? Okay, great. Sure. Gary.
I read where they were able to tell the concentration of CO2 in the ancient times by looking at fossil plant leaves and the number of stomata on the leaves.
Oh, yeah.
Is there any evidence of that happening, and does that affect the biomass taken up by the plant?
Well, so I have done some work in elevated carbon dioxide experiments, and increasing carbon dioxide does tend to increase plant biomass. It does tend to increase the amount of carbon taken up by plants. I know that's only part of your question. And whether or not that's a long-term trend or not depends on several different factors, like whether or not there are enough nutrients involved and water, for example. But the stomate question, with the experiments I've looked at, I don't think people have looked at that, at least not in the one that I'm familiar with. And I would have to look into that, but that's a really good question.
And a follow-up is, there's some local farmers or people claiming that they can, quote, farm carbon by building topsoil
Yep.
And absorbing carbon that way, and then
Yep.
we can just absorb all the carbon we're producing and everything's fine. What do you think of that idea?
I have seen some fairly dramatic claims that I would love to see some data for. Building soil carbon is not typically thought of a very easy thing to do. So it's more of a long-term process generally. At least that's what we think. I know they're claiming like less than a year, I think, right? And I know there's actually people who have put in some grants to try to investigate that with some actual data. And I may or may not be involved in that, but I would be very interested to see what exactly is going on those farms. Hi.
Could you talk a little bit about the projects that you had where you're modeling decomposition?
Sure.
And how that relates
Sure.
to the rest of us?
Yeah, definitely. So this is work I've been doing for probably a decade now. Just using really large-scale data sets from across the world at this point to try to figure out the best and simplest way to model carbon dioxide release from litter in this case. And the way that really ties in is trying to figure out, what are really the important drivers of this process, because it is a really large flux, and if we change it a little bit, how is it going to increase or decrease? And actually, one of the really fun things is that one of the people that I do some of this work with runs one of these giant ecosystem carbon models that models everything across the whole world. And it's recently getting incorporated into one of the IPCC models. So the work that we do informs this model, which will then inform predictions about climate change, which is really exciting.
Is that only forest litter, or are you also looking in grass?
No, this is all kinds of litter. So it depends on which data set. But across all of the data sets, it's everything from grass to roots to deciduous litter to conifer litter, tropical forests, temperate forests. It's a huge data set. It's very cool. So we're really looking for how much detail do we need for these to describe these really broad scale patterns.
Thank you very much.
Sure.
think I figured it out.
You're more agile than I
Oh,
was.
not necessarily. Okay, great.
All right.
Okay, so I'm Paul Hines, and this is so I'm sort of changing gears here from the ecological side of things to the more engineering side of things. But I do a lot of work related to how electricity works, and electricity is a big portion of the problem. So about 40% of U.S. Greenhouse gas emissions come from power plants, and so obviously power plants are part of the problem. Another big chunk of the problem that's going to get us well above 50% of the problem as far as greenhouse gas emissions is going to be electric vehicles. And so today I'm going to talk a little bit about power plant emissions and electric vehicles and kind of bring those together a little bit, or about vehicles and electric vehicles. Okay, so a lot of people advocate for wind and solar power as part of the solution. So power plant emissions are high largely because we rely very heavily on coal in the United States for our electric power. About 50% of electric power comes from coal. In New England, it's quite a bit less than that, but we still use some coal power. And so wind and solar are fabulous because they do not, so there's no smokestack on your wind turbine here, so there's no emissions from the wind. But they have some other effects that we need to think about as far as integrating wind power into the electric system. Similarly, solar farms have no smokestacks, and so they also have that benefit. And for both of them, costs are coming down, particularly with solar right now. So wind costs have been fairly stable recently, but solar power has been coming down really rapidly as Chinese manufacturing has increased and as European subsidies have gone down, which has sort of increased the supply relative to the demand. There's a problem. So the electric grid was really designed to handle electricity from coal plants and nuclear plants and a few natural gas plants. And so coal plants are really boring. When you turn them on, they basically kind of do what you expect them to do, and you turn them down, they turn down. And so they're not very exciting power plants. Nuclear plants are the same way. When you turn on a nuclear plant, it kind of goes until it's done, and then you turn it off. Wind and solar are much more interesting. As a power engineer, this is much more exciting. So now when I turn on my solar plant, it goes on and off, on and off, on and off all day long, which is really interesting. Unfortunately for the power grid, that's actually creates a lot of challenges for incorporating this type of electricity into the system. So anyone know why it's going on and off so rapidly through the day?
Can't store it.
Well, so we can't store it, so that's the problem. And storage is the problem. So why is it fluctuating?
So what are changing throughout the day?
Clouds, yeah. So as clouds come through, the power goes up and down with the clouds. Storage is the sort of obvious solution. However, electricity that comes out of the wall socket comes out in form of a wave, and so it's coming up and down, back and forth out of the wall socket. And so you can't store waves, so we need to convert it into something else in order to store the electricity. We can use a battery, you can pump water up a hill. So there are some things you can do to storage, but those are still pretty expensive. And so again with wind comes and goes when it wants to, sometimes even more dramatically than solar. And so this is wind over, I think, 10 or 20 days. That's 10 days. And so wind from a wind plant is going to come and go, which means it's similarly, just like the solar, going to be pretty challenging to integrate into the grid. So the question is, how do we take these resources that come and go when they please, integrate them into a power grid that was really designed for coal plants and nuclear plants that are rather boring? Okay, so a lot of people have been talking about smart grid in the last few years. And smart grid is kind of this big amorphous term that refers to lots of different technologies. And the vision of smart grid is really to kind of make the power grid, which was designed 100 years ago plus, to work a little bit more like the internet. What's great about the internet is that there's probably 200 devices that are connected to the internet right now. Lots of different devices can connect. They can disconnect and reconnect without any trouble. You can do lots of different things on the internet, and the internet doesn't care, which is really great. So we'd like the power grid to do the same thing. We can plug in solar panels, electric vehicles, smart washers, lots of different devices into it, and make the power grid work better rather than work worse. And so thus far, however, Smart Grid really has done a great job of producing fancy graphics from the Department of Energy. In actuality, it's a fairly limited set of technologies, and people aren't quite exactly sure what Smart Grid will do for us. So let me mention just 2 or actually 3 technologies that can kind of come together, and then we'll think about, in one particular problem, how we might use these technologies to make electricity work better. So the smart meter is kind of the focal point for the consumer side of the smart grid. And how many people have actually gotten their smart meter? And so in Burlington, they're going out right now. I think we got ours this weekend. And all it is a meter that's, instead of measuring your electricity consumption once a month, it's going to measure it every 15 minutes. And the advantage is that now they can begin to give you incentives to consume electricity at times that that are less expensive or less costly in terms of emissions relative to times that are more expensive. And so on a hot summer day, we're probably consuming power from every single coal plant in the system, every diesel plant, everything that we can possibly turn on will be turned on the hottest summer day. In a midwinter evening, we're probably using a lot of hydro. We're probably using McNeil, which is a wood-fired power plant, other things that are less costly. And so if we can begin to give consumers incentives to adjust their consumption based on cost and emissions, hopefully we can do a little bit better. Electric vehicles can become a part of that because if you're going to charge your vehicle, you can charge it at different times of the day. So that's kind of a good thing. And similarly with air conditioners, we can adjust the timing of air conditioning load based on the price of electricity or based on some other factors, how much wind or solar there is available, which will ultimately affect price. So we can adjust this load based on the time of the day and the price and the emissions. So in one research project that I worked on actually with a student from Rubenstein, and I did this together, we were trying to imagine a world in which there were 10 years, so we were thinking about 10 years now. We actually modeled 2020. We did a model of New England as well as the mid-Atlantic United States. And we were trying to think about what happens when there's lots and lots of electric vehicles in the system. And so we were, I think we had 5%, 10%, and 20% of all vehicles were electric vehicles. And then we capped carbon dioxide emissions. So we imagined that there's sort of this fairly restrictive cap on carbon dioxide emissions. We went up to a 50% cap. And so we're actually going to cut carbon dioxide emissions from the electricity sector by up to 50%. And then we assumed we had 2 different cases. In one case, people did not respond to price. And so as the price of electricity went up, people didn't really change their consumption patterns. And then in the other case, they were responsive. And so we're assuming then that there's technology available so that people can adjust their consumption based on the price of electricity. And then this carbon cap is going to affect the price. And that's what carbon caps of anything do. They create scarcity, which increases prices. And our question was, how much would it cost? How much would it cost to get us to a fairly extreme change where we're reducing CO2 by 50%, we have maybe 20% electric vehicles, and yeah, so how much would it cost? And also then the other thing that we did in this modeling exercise is we allowed the system to build new power plants. And so it could build new wind plants, or it could build new gas plants, or it could build new coal plants. So there's a ton of data on this slide, but let me just give you a few little highlights from here. So what I've done here is we've got lots of different scenarios, and I've measured how much new power plant capacity, John and I measured how much power plant capacity was built in these various scenarios. And what's interesting is that this is the case, the kind of non-smart grid case. And so in the non-smart grid case, what you see is roughly, this is sort of business as usual. And this is on the other extreme, lots of electric vehicles and a 50% reduction in CO2. So this is 50% reduction in CO2, 30%, 10%, nothing. These scenarios are how many electric vehicles. And so what we found with the non-smart grid case is that we would have to build a lot of wind to reduce CO2 by 50%. So this is how much wind we had to build. This is a little bit of natural gas, and you basically have to build the natural gas in order to fill in the gaps in the wind power. And so we had to build a lot of wind in order to get to this 50% reduction scenario. And the price of electricity really went up dramatically. And so we're well over doubled the price of electricity, which actually isn't all that unreasonable, but it's a pretty significant change. In the smart grid scenario, we were able to get that same reduction in CO2 without building any power plants, which really actually surprised me. I had no idea that we would get that result. And the increase in electricity prices was really quite modest, about a 50% increase in average prices. There's still some extreme days, but you actually also decreased the extreme changes in the price of electricity. And so your electricity prices, instead of fluctuating by a factor of 10 on some days, they'd only fluctuate within a range of a factor of 2, which is a much more sort of reasonable scenario. And so what happens, what we conclude from this is that if you are able to enable people to respond to price fluctuations, then we can make more dramatic reductions in carbon dioxide, as well as support a fairly high penetration of electric vehicles. So that's one particular project that I'm working on related to smart grid and climate change. There's a number of other projects that I'll just kind of mention right now. On the more engineering side, electric vehicles, if we had lots and lots of them in the system, would begin to create stress in the grid. And so we've been working on some technology to actually mitigate the stress so that when people, all the electric vehicles don't charge at the same time. So that's kind of fun technology project. And then another project that's actually really, really interesting that I've been doing with a computer scientist right now called Josh Bongard. He and I have been trying to figure out how can we encourage people to ask good questions of one another so that they can teach each other about energy efficiency. And this is an idea that we've actually tested in an online social network. It was sort of moderately effective on our first round with energy, but was really effective for body mass index. And so we had students asking each other questions about what factors might influence body mass index, and came up with some really counterintuitive predictors of body mass index. And so now we're going to do that same thing in Burlington coming about, I think probably starting in January. If you have a smart meter in Burlington, you'll get an invitation to participate in an experiment in which you'll ask questions of your neighbors about electricity consumption and help you, hopefully, understand better what makes one person consume more electricity relative to another. That's it. I have time for a couple questions, hopefully.
Questions? Yes.
Do you know if there's any chance of a battery coming out to sort of make the renewable energy more reliable?
Batteries, yeah, so batteries are great, and you can definitely do it. So I've taken a tour of a 2 megawatt battery, which is about the size of like that big. And so they're building the batteries that are that big, and they're deploying them in the grid. But they're really expensive. And so right now they're really building them as parts of research projects funded by the Department of Energy. They're not really cost competitive enough to make it worthwhile. But if we were to end up in a really high wind and solar penetration scenario, you'd probably need them in order to make the grid work. So that's, and then maybe cost would come down as well.
How are electric vehicles more efficient than gas-powered vehicles? Because it still requires the energy sources or anything from the grid to charge electric vehicles, and through that, like, there's still energy loss through that whole transfer and everything.
So there's about, I think it's important to note where the energy losses are. And so as far as the energy losses in electric vehicles, most of the loss is in the conversion from whatever the fuel is to electricity. So that process can be somewhere between 30% and 60% efficient. And then another 5 to 10% is lost in moving the electricity from the power plant to your home. So that's a fairly small loss. But in combustion, it's about 60% of the energy to 80% of the energy is lost in burning it in your engine. So it turns into heat, and then a little bit turns into motion. And so they're more efficient because electric motors are really highly efficient. So they're over 90% efficient. So electric motors are quite efficient. And then the best thing about electric vehicles is that it gives us flexibility. So with liquid fuels, unless we come up with a really great biofuels option, you don't have any options as to where your energy comes from. But with electric vehicles, just like with my graphs there, you have choices. So we can get that electricity from coal, or we can get that electricity from natural gas, or we can get it from wind and solar. So it gives us the choice of how to fuel our transportation.
Any other questions?
Amy?
So
Yeah.
I see that you didn't include, or did I miss it, nuclear at all in the future portfolio.
Right.
Can you talk about why you'd made assumption of no new nuclear in the New England regional grid?
The biggest reason is that new nuclear looks quite expensive because, I mean, it's definitely out there and manufacturers are advertising low costs. But if you actually look at projects around the world from the last 10 years, they've ended up with really high costs. And so we decided not to even include it. We could have included it, but it would have chosen coal over the nuclear. Or natural gas over the nuclear, most likely. So that's the main reason, not for any other choices.
Do you see any future improvements in terms of technology for natural gas, especially hydrofracking, in the near future?
Fracking has a big influence on electricity. So right now, electricity prices are extremely low because natural gas supplies are so high. And so it does have a big effect on electricity. And natural gas power plants tend to be quite efficient because they're built in 2 cycles. And so you can make them about 60% efficient. But it's, obviously there are environmental issues associated with fracking. But the biggest effect on electricity right now is that they're making prices really, really low. And so this smart grid stuff is actually looking really expensive because electricity is just dirt cheap. So,
Okay.
thanks.
Thanks, Paul.
Are these being recorded, or is this just make our voices carry?
Being recorded via video. Is that okay?
Yeah. I don't need it. It's not being recorded. All right, so we've gone from ecologists to engineers to economists, and I'm actually I'm giving kind of a general presentation that covers a lot of my research, so it's kind of a mile high. Let's see if this is, there we go. So I do want to focus on, my title actually kind of stinks too, Financing Agroecology. This is a specific project I'm doing in Brazil, but I'm going to talk about a bit more than that. So I do want to talk about agriculture and climate change. So, the greatest threat from climate change is agricultural production. We've had this, uniquely stable period, the Holocene, for the past 10,000 years, in which agriculture and civilization emerged, and it seems that we depend on that stability for our agriculture. Conventional ag, and especially cattle, contributes about 1/3 of greenhouse gases right now, which is nitrous oxide, methane, CO2, also from land use change and the energy use in ag. Historically, ag would take about 1 calorie of energy to create about 10 calories of food energy. Now we use about 10 calories of hydrocarbons to put 1 calorie of food on your plate. So from that perspective, we've developed the least efficient agricultural system in planetary history. Question is, does agriculture matter? And I say I'm an economist. Here's actually a fairly conventional economist view. So this is Nobel laureate Thomas Schelling, who says agriculture really only accounts for about he says agriculture and forestry, but agriculture alone is about 1% of our GNP. So if we lose 30% of agricultural output, no harm done. Because, you know, a dollar is a dollar is a dollar. If we lose 30% of 1% of our GNP, no harm done. So they missed the big point that some things are essential and have no substitutes, and food is absolutely one of those things. You know, I'm kind of dismissing offhand this view. I am very interested in these critical thresholds. So anytime something is essential and has no substitutes, that means there's a critical threshold. There's a certain level we need to absolutely survive. So one example is for food, agriculture. There's a physiological threshold. If you don't get at least 1,500 calories per day, you are going to start suffering from malnutrition, eventually starvation. You're going to be less developed than you would be. You know, really, it's a very serious issue. There are also climate thresholds. So in climate thresholds, I'm going to talk about two different thresholds. One is what is the stock of atmospheric carbon dioxide that's going to lead to serious disruptions. So there's an atmospheric threshold. And a lot of scientists believe that atmospheric CO2 concentrations greater than about 350 parts per million will lead to serious disruptions to our climate system. The current stock is about 391 parts per million. There's apparently about a 30-year time lag between the level of CO2 in the atmosphere and when we experience the climate you would feel from that. So the climate change we're experiencing now is associated with less than 350 parts per million. We only reached 350 parts per million about 1990. And by the time the oceans absorb the heat and everything, so for various reasons, we are experiencing a level of climate change less than 350 parts per million would feel like. And there's two different types of thresholds with atmospheric stocks. There's an ecological threshold. If the stock gets high enough to warm the climate, it could lead to runaway climate change. Melting of the ice cap so that we get more absorption of heat, less reflection, release of methane from the tundra, et cetera, so that we'd get this ecological threshold where the atmosphere heats to a certain level that creates positive feedback loops and the release of more climate change gases and runaway climate change, so we get a system spiraling out of control. Another threshold we could think of as an economic threshold. Perhaps at 350 parts per million, we're not going to get runaway climate change, but we're going to have enough instability that we can no longer count on agriculture, which is essential for sustaining our civilization and 7 billion people. So I would say an ecological threshold is crossing, to runaway climate change. An economic threshold is creating conditions that are no longer sufficient to sustain the global population. There's also another type of threshold, which is a flow threshold. So, in a bathtub, anytime your flow in is greater than your flow out, the bathtub fills up. And if it keeps going, it overflows. So the flow threshold is anytime your CO2 emissions are greater than your absorption capacity. And so when we're putting CO2 emissions into the atmosphere faster than our ecosystems are sequestering them back out. And currently, we're exceeding sequestration capacity. We're putting CO2 into the atmosphere about 5 times faster than it's sequestered out by all the ecosystems. So we've got this steady buildup of CO2. And per capita emissions in the US, if we had an equal access to the global atmosphere and all countries had to bring their flow levels down to the absorption capacity, we'd have to reduce our emissions about 95%. So the point is, anytime your flow exceeds this critical threshold, your stocks will accumulate and eventually exceed that critical threshold. So what we need to do, whatever stock level we choose to target, we have to reduce our emissions by at least 80%, or else somehow stimulate sequestration elsewhere. So I actually, showing what these thresholds look like, I just used some readily available data on the internet to show a demand curve for food. So your demand curve in economics is the marginal benefits you get from an activity. And all I did here, this is calories per day. Each of these dots represent different countries. And so calories per day is your quantity. The relative price, this axis is supposed to be price, but prices are very, very different. If you're here in Zambia, for example,